Hi everyone. In this video, we are going to discuss valence bond theory. Valence bond theory is developed by Pauling to know the bonding in metal ligand complexes. This is the first theory. Basically, there are three theories which is used for explaining the nature of bonding in transition metal complexes. They include valence bond theory, known as VBT, crystal field theory, known as CFT, ligand field theory, LFT. Ligand field theory is also known as molecular orbital theory or adjusted crystal field theory. So moving on to valence bond theory. So basically valence bond theory, we can see it as two parts. One is some points describing about the metals, and the other is some points describing about the ligands. So first, moving on to metals. So the metal, that is the central metal atom or the central metal cation, it should have enough or a number of vacant orbitals which is produced from s, p and d orbitals, and how many vacant orbitals are available, that will be contributing towards the coordination number to form covalent bond. So basically in VBT, the metal ligand bonding will be covalent bond. The second point is there should be a maximum overlap between the metal and the ligand, so the bond will be stronger. And how many number of atomic orbitals of the metal are getting hybridized, so same number of equivalent bonding molecular orbitals known as hybrid orbitals are produced. So the properties of hybrid orbital is they'll be having same geometry, same energy, and they will be having more directional property. As we all know, s orbital is a non-directional orbital, but p orbital and d orbital, they are having directions. So when their hybrid orbitals are producing, they will be having a definite direction which will be pointing towards, in such a fashion the ligands will be easily approachable. Then the third point is the metal atom or the metal cation should have vacant orbitals. So then only the incoming ligands will be able to give their filled orbitals to produce a coordinate bond between metal and ligand. So there should be a vacant metal or hybrid orbital, and the ligand should have fully filled orbitals. Then the magnetic moment and the coordination number of the metal atom will be deciding the hybridization and geometry which is followed by the complex. Then another point is the 2D and 3D transition, that means the second and third period transition metals will be having, they will be forming bonds with n-1d orbital. So basically these 2D and 3D metals will be producing inner orbital complexes, and the outer, because inner orbital complexes will be having more, they will be producing more stable bonds. The outer d orbitals, they are in the most diffuse form, so it is very difficult to produce bond with them. Then the last point is, if one or more unpaired electron is there, then that complex is considered to be paramagnetic. Moving on to the ligands. The ligands are of two types. One is strong field ligand and the other is weak field ligand. Strong field ligand is also known as strong electron donating ligand, and weak field is also known as highly electronegative. They will be highly electronegative elements. Then strong field ligands are having examples of Cn-, CO, etc. And weak field ligand examples are fluorine, chloride ion, then all the ligands which is having oxygen in them, like OH-. Then strong field ligands will have a tendency to pair the d electrons of the metal cation, but weak field ligands, they will not pair the metal d electrons. So whatever be the configuration of the metal will be remaining same because no pairing is there. Then strong field ligands will be forming covalent bond with the metals, but weak field ligand, it will not form covalent bond, but the bond formed by weak field ligand with the metal is always a ionic bond. Then coming on to the hybridized products, like metal and ligand will be producing some complexes. The complex can be octahedral complex, tetrahedral complex and square planar complex. If the metal and ligand are combining to produce octahedral complexes, Octahedral complexes can exist in two different hybridization like D2sp3 and sp3d2. D2sp3 means inner d orbital is used for the complex formation, and sp3d2 means outer d orbital is used. If inner d orbital is used to form an octahedral complex, the complex will be more stable, and the d orbitals involved in that in both the cases, in inner orbital complexes and in outer orbital complexes, the d orbitals involved will be dx square minus y square and dz square. In the case of tetrahedral complexes, sp3 hybridization and sd3 hybridization is seen, where the d orbitals used are dxy, dyz and dxz. When they are forming square planar complexes, like dsp2 is the main common hybridization seen, like dsp2. But in the square planar complexes, sp2d is also seen only in very few complexes, especially the ones which I have mentioned here, copper complexes, in which copper is having 9 D9 configuration, and these complexes which I have listed, they are very important complexes. Thank you.